Hello everyone, welcome to the April 16th edition of Calc 2. Reminder that you have a web assignment due tomorrow, which is Friday. So today's an exciting day. You get to learn about a new way of graphing functions. Up until now, you have been graphing a function, representing a graph, by a single equation involving two variables, y and x. In this section, we're going to learn about situations where you use three variables to represent a curve. So here are some functions that you are familiar with. You've seen functions that look like y equals x squared and y equals x cubed. So these are functions that you can graph. What about some other graphs, such as this, or this, or this? Are these graphs of functions? No, why not? It's because they do not pass the vertical line test. Therefore, we need another way of graphing these more complicated looking curves that are not graphs of functions. Okay, so let's look at a new situation. So let's suppose we are following the path of Dr. Carroll. And we know that his location at time t is t squared t cubed. Let's see where he is at certain points in time. Well, let's have t, his x coordinate, and his y coordinate. And let's say that t runs from negative infinity to infinity. So we'll pick a couple values and see what happens. So I plug t into the equation for x, and I get 4 minus 8, 1, negative 1, 0, 0, 1, 1, 4, 8. So let's graph these points. All right, so let's plot his point at t equals negative 2. That should be at the point 4, negative 8, down here. At the time t equals negative 1, he should be right here. And here, here, and here. And so if I kind of graph this curve, it should look something like this, where Dr. Carroll is traveling in this direction. So that is the graph of Dr. Carroll's path. And we call this a curve defined by parametric equations. So a parametric equation is one where your x and y coordinate, in this case, are given by functions of a third variable t. T is often time. So if f and g are continuous functions of t on an interval I, then the equations x equals f of t and y equals g of t are parametric equations, and t is the parameter. All right. So the set of points that arises as t runs through values in our interval I is the graph of the parametric equation. And we call this a plane curve, often denoted by C. All right, so I want you to do a graph of a parametric equation to draw the plane curve. And so I'm going to give you some equations. And I'm going to give you the interval I. So t will go from 0 to 2 pi. So I want you to take a minute to pause the video, plug in a bunch of values of t, and graph what this is equal to, or what shape this makes. All right, now that you've had a chance to do that, let's plug in some values. So I will have my t value, x, y. So let's do 0, and the cosine of 0 is 1, 0. Let's do 0 pi, excuse me. Let's do t of pi over 4. That's root 2 over 2, root 2 over 2. Pi over 2, 0, 1. 3 pi over 4, that's negative root 2 over 2. Root 2 over 2, and then let's just finish this up. 3 pi over 2, that's negative 1, 0. Sorry, excuse me, that's not what I want. I want this to be pi. 3 pi over 2 and 2 pi. So let's plot these points. 1 half, negative 1, negative 1 half, 1, 1. So our first point is right here. Our next point is right about here, 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 here. And you can probably guess what this shape is now. It's a circle. So though this parametric equation right here gave us a plane curve that was a circle. So this is great. We have a new way of giving the path of an object. And we can sometimes identify what shape are we going to get before we actually graph it all, because that's very time consuming. So there's a process called eliminating the parameter that helps us figure out what's the shape of our graph without actually plugging in all the values. So this process is one where you find a rectangular equation that represents the graph of a set of parametric equations. And when they say rectangular equations, they mean in y and x. This process is called eliminating the parameter. So let's take a look at the example we just did. In the example we just did, we had x equal to the cosine and y equal to the sine. So what do we know? We know that the cosine of t squared plus the sine of t squared is always equal to 1. That's a trig identity. But what we notice is the cosine is the same as x, and the sine is the same as y, which tells us that x squared plus y squared equals 1, which is the equation of the circle. Warning. the plane curve from the parametric equation might only be a subset of the rectangular equation we find. Okay, so let's take as an example and see what we mean by that. So let's look at the same parametric equation as before. And I want you to take a second and identify, what does this look like? Well, I think what we can all find is that it looks like a semicircle. This is not the full circle. We're missing this piece right here. So even though x squared plus y squared is still equal to 1, the actual plane curve only is the semicircle, because this range of t values is very important. And so when you find the rectangular equation, it might only be, that might be bigger than the actual plane curve. Okay. So doing what we did right here requires us to adjust the domain. So here, in this previous example, this is the equation of our parametric curve, our plane curve, but we have to add the restriction that y is bigger than or equal to 0, because down here, this is where y is less than 0, and that's not part of our plane curve. Okay, so let's do some other examples. Let's find the rectangular equation for x equals root t and y equals t minus 1. Sorry, t minus 5. Okay, well, it's not so hard to see that this should become, well, y is root t squared minus 5, which is x minus 5. So this should tell us that our rectangular equation is x squared minus 5. But what do we notice? X must be positive. We're only getting the positive half of the parabola, so we have to restrict the domain to x being positive or maybe 0. Now here's an example for you guys to do at home. Find a rectangular equation for x equals e to the minus t, y equals e to the 2t plus 2. Remember to restrict the domain. Okay, so let's look at this example up here and take a look at it using Desmos. So Desmos is just very easy to do parametric equations. You just type it in here. And you give like a range of t values. Let's do to 100. And you see that you get half of the parabola. Oops. So you see that this red curve is exactly the right half of the parabola, but the left half is missing. All right, so let's go back here and do a little bit more. So trig identities are useful for eliminating the parameter. Let's do an example. Let's look at the curve x equals 4 cosine of t y equals 3 sine of t, where t runs from 0 to 2 pi. So at first, you think, well, there's only one trig identity that I know. It's the cosine of t squared plus the sine of t squared is 1. However, what's the cosine of t? Well, I think you'll find that the cosine of t is the same as x over 4, and the sine of t is the same as y over 3. So what this tells us is that this becomes x over 4 squared plus y over 3 squared equals 1. Or in other words, this is x squared over 16 plus y squared over 9 equals 1. And what's this the equation of? We know from the previous section, this is an ellipse. So I'm going to have you try one. For in your notes, I want you to find the rectangular equation for x equals 2 secant of t, y equals 3 tangent of t. And we'll let t go from, I think, negative pi over 2 to pi over 2. Okay, so work that one in your notes. So I'm going to do a couple others. I'm going to see if you can find equations for them. So let's look at this one. And let's look at this one. So can I find parametric equation for this curve? Well, there's a trick to doing these. So let's look at the x values, what's happening, and let's look at the y values with what's happening. The x value starts at 0. It goes up to 1 and goes back down to 0. The y value starts at -1, goes up to 0, and goes up to 1. What functions do these look like? Well, the x one, this looks a lot like the sine, and the y looks a lot like the negative cosine. And that's exactly what's going to happen. So our parametric equations are x equals the sine of t, and y equals negative the cosine of t. And it's not so hard to see that t will go from 0 to pi. So now I'm going to have you guys do a couple of these. Find the parametric equation for the following two curves. Okay, here's the first one. I want you to do the circle where you start right here, but you go clockwise. We did counterclockwise before. And let's say t will go from 0 to 2 pi. Here, I want you to do the normal circle where you start here, but you go around twice. This one's a little tricky, and I still want your t values to go from 0 to 2 pi, but see if you can write down a parametric equation where your t values will go from 0 to 2 pi, but your curve goes around the unit circle twice. Let me know if you have any questions, and I'm happy to help.